Procedural steps for evaluating definite integrals. Okay, let's begin. Welcome back. So, in the previous sections, we've laid down the why behind definite integrals, the second fundamental theorem of calculus. Remember, that theorem tells us that we can find the definite integral using an antiderivative, but it doesn't necessarily tell us how to actually do it. This tutorial is all about the how. We're going to focus on a practical, step-by-step procedure to calculate the value of a definite integral. We'll move beyond the theory and get our hands dirty with the calculations. Now recall that a definite integral, written as integral from a to b of f of x with respect to x, and that's how I'll refer to it going forward, represents the signed area under the curve of the function f of x, between the points x equals a and x equals b on the x-axis. The a is the lower limit of integration, and b is the upper limit. It's important to remember the signed part. Areas above the x-axis are positive, and areas below are negative. To determine this numerical value, that signed area, we'll be following a systematic two-step process, which we'll break down in detail on the following slides. So, keep that two-step process in mind as we move forward. We'll first find an antiderivative, and then we'll evaluate it at the limits of integration. Step 1. Find the indefinite integral, the antiderivative. Okay, so let's move on to step 1 of evaluating definite integrals. As we discussed on the previous slide, we're building on the second fundamental theorem of calculus, but now we're focusing on how to actually calculate these integrals. The very first thing we need to do is find what we call the antiderivative of the function f of x. Think of it like this. Integration is the reverse process of differentiation. So, the antiderivative, which we denote as capital F of x, is a function that, when you take its derivative, that is, when you find f prime of x, gives you back the original function, f of x. Now, when we're finding indefinite integrals, that is, integrals without specific limits, we always add a constant of integration, usually denoted by c. This is because the derivative of a constant is always 0, meaning there are infinitely many functions that could have the same derivative. So, we write the indefinite integral of f of x as f of x plus c. However, and this is a crucial point, when we're dealing with definite integrals, the kind with upper and lower limits, we don't need to worry about that constant c. Why? Because it will cancel out when we get to step 2, which is evaluating the difference. Let me show you what I mean. If we did include the constant, the calculation would look like this. We would have f of b plus c, minus f of a plus c. If we expand that, we get f of b plus c, minus f of a minus c. Notice what happens. The plus c and the minus c cancel each other out. So, we're left with simply f of b minus f of a. Because of this cancellation, we can save ourselves a step and just ignore the constant of integration, c, when calculating definite integrals. It simplifies the process without affecting the final answer. Remember this, as it's a common mistake students make. We'll be applying this in the examples coming up, so make sure you understand this concept thoroughly. Step 2. Evaluate the difference, applying the limits. Okay, so we've successfully found the antiderivative in the previous step. Now, let's move on to step 2, which is all about applying those limits of integration to get our final answer. As you recall from the definition of a definite integral, we're trying to find the area under the curve of a function, f of x, between two specific x values, a and b. A represents the lower limit of integration, and b represents the upper limit. These values define the interval over which we're calculating the area. Now, to show that we're evaluating the antiderivative at these limits, we use a specific notation. We write the antiderivative, which we've called f of x, inside square brackets, with the upper and lower limits written as a subscript. So the integral from a to b of f of x dx, that's read as the integral of f of x with respect to x from a to b, is represented as f of x, enclosed in square brackets, with a and b written below it like this. F of x with a subscript a to b. This simply means we're about to evaluate f of x at b and a. To actually find the numerical value of the definite integral, we substitute the upper limit, b into the antiderivative, f of x, and then subtract the value we get when we substitute the lower limit, into the antiderivative. Mathematically, this is written as value equals f of b minus f of a. Now, this is extremely important and a very common mistake students make. Always subtract in the order of upper limit minus lower limit. So, it's f of b minus f of a, not the other way around. If you reverse the order, you'll end up with the wrong sign for your answer. Remember, we're dealing with signed area, and the order matters to ensure we get the correct result. We'll see this in action with some examples on the next slides, but keep this step firmly in mind. Find the antiderivative, evaluate it at the upper and lower limits, and subtract the lower limit value from the upper limit value. That's the key to unlocking the value of a definite integral. Illustrative examples. Okay, let's move on to our first example. This will really solidify the two steps we just discussed. Here on the slide, we're asked to evaluate the definite integral of 3x squared plus 2x, with the limits of integration being from 1 to 3. So, we have the integral from 1 to 3 of 3x squared plus 2x with respect to x. That's what the dx signifies. Now let's begin with step 1. Finding the antiderivative, which we've denoted as f of x. Remember, the antiderivative is a function that, when you take its derivative, gives you back the original function. To find the antiderivative of 3x squared plus 2x, we'll use the power rule for integration. The power rule states that the integral of x to the power of n is x to the power of n plus 1, all divided by n plus 1. Applying this to our first term, 3x squared, we get 3 times x cubed over 3. The 3's cancel out, leaving us with x cubed. For the second term, 2x, we have 2 times x squared over 2, and again the 2's cancel, giving us x squared. Therefore, the antiderivative f of x is x cubed plus x squared. Don't forget, we don't add a constant of integration. See, when dealing with definite integrals, as we discussed on the previous slide. Now let's move on to step 2, applying the limits of integration. This is where we evaluate our antiderivative at the upper and lower limits and find the difference. We represent this by writing our antiderivative, x cubed plus x squared, within square brackets, with the limits of integration written as superscripts and subscripts. X cubed plus x squared from 1 to 3. This notation means we'll evaluate f of 3 and then subtract f of 1. Let's calculate f of 3. We substitute x equals 3 into our antiderivative. 3 cubed plus 3 squared, which is 27 plus 9, giving us 36. Next, we calculate f of 1. Substituting x equals 1 into our antiderivative, we get 1 cubed plus 1 squared, which is 1 plus 1, equaling 2. Finally, we subtract f of 1 from f of 3, 36 minus 2, which equals 34. Therefore, the definite integral of 3x squared plus 2x from 1 to 3 is 34. And that's our final answer. Keep in mind, as we move forward, that this process, finding the antiderivative and then evaluating the difference, is the core of evaluating definite integrals. We'll see this applied in more complex scenarios and even in real-world applications, as you'll see in the next example. Illustrative examples. Okay, let's move on to another example, this time applying definite integrals to a real-world scenario. As you know from the previous slides, we've mastered the procedural steps, and now we're going to see how it all comes together. This example involves physics. We're told that a particle is moving along a straight line, and its velocity is given by the function v of t, equals 4t plus 5 meters per second. Our task is to find the total displacement of this particle between time t equals 0 and t equals 2 seconds. Now, remember from your physics classes, displacement is essentially the change in position. And, crucially, displacement can be calculated using a definite integral of the velocity function over the given time interval. So, mathematically, we represent the displacement as the definite integral from 0 to 2 of the velocity function, 4t plus 5, with respect to t. We write that as integral from 0 to 2 of 4t plus 5 dt. Let's now follow our two-step process. Step 1 is to find the antiderivative of the velocity function, which we'll call f of t. So we need to integrate 4t plus 5 with respect to t, applying the power rule for integration. Remember that the integral of x to the power of n is x to the power of n plus 1 divided by n plus 1. And integrating each term, we get 4 times t squared divided by 2, plus 5 times t. This simplifies to 2t squared plus 5t. Therefore, our antiderivative, f of t, is 2t squared plus 5t. Step 2 is to evaluate the difference between the antiderivative at the upper and lower limits of integration. We write this as f of t evaluated from 0 to 2, which looks like this: 2t squared plus 5t, with the limits 0 to 2. Finally, we calculate f of 2 minus f of 0. Let's start with f of 2. Substituting t equals 2 into our antiderivative, we get 2 times 2 squared plus 5 times 2, which equals 2 times 4 plus 10, which simplifies to 8 plus 10, giving us 18. Next, we calculate f of 0. Substituting t equals 0 into our antiderivative, we get 2 times 0 squared plus 5 times 0, which equals 0. Now we subtract. 18 minus 0 equals 18. Therefore, the total displacement of the particle from t equals 0 to t equals 2 seconds is 18 meters. And that completes our example. Remember, the key is to consistently apply the 2 steps. Find the antiderivative, and then evaluate the difference at the limits of integration. We'll be looking at common mistakes in the next slide, so pay attention to those to avoid them in your own work. Common mistakes to avoid. Okay, let's move on to slide 6. This slide highlights some common mistakes students make when evaluating definite integrals, and being aware of these before you attempt the problems can save you a lot of frustration. 1. Incorrect order of subtraction. The first, and surprisingly frequent, mistake is getting the order of subtraction wrong. Remember, when we evaluate the definite integral, we're finding the difference between the antiderivative at the upper and lower limits. So, you must calculate f of b minus f of a. If you accidentally do f of a minus f of b, you'll get the correct magnitude of the answer, but the sign will be flipped, meaning your answer will be wrong. It's a simple mistake, but a critical one. 2. Sign errors during subtraction. This one builds on the previous point. Sometimes when you evaluate the antiderivative at the lower limit, f of a, you might get a negative number. Students often forget to properly handle the subtraction in these cases. For example, let's say f of b is 10 and f of a is negative 5. The correct calculation is 10 minus negative 5, which equals 15. A common mistake is to treat it as 10 minus 5, which would only give you 5. Remember, subtracting a negative number is the same as adding its positive counterpart. Pay close attention to those signs. 3. Applying limits to the original function. This is a conceptual error. It's vital to remember that you always substitute the limits of integration, a and b, into the antiderivative, f of x, not the original function. F of x, we find the antiderivative first, and then we apply the limits. Don't skip that crucial first step. 4. Ignoring the antiderivative step. Finally, and this is a fundamental error, attempting to calculate the area, or the definite integral, without first finding the general indefinite integral, the antiderivative, is simply impossible using the Fundamental Theorem of Calculus. The whole process relies on finding that antiderivative as the first step. You can't jump straight to plugging in numbers. You need that f of x to begin with. So, keep these common pitfalls in mind as you practice. We'll now move on to the final slide, which summarizes the key takeaways from this tutorial. Key takeaways. Okay, let's recap everything we've learned about evaluating definite integrals. This is our final slide, and it's all about solidifying the key takeaways. First point, the process. The evaluation of a definite integral is a two-stage process. Think of it as a sequence. First, we perform the integration, that is, we find the antiderivative of the function. Then, we move on to the evaluation stage, where we apply the limits of integration and calculate the numerical value. So, it's always integration then evaluation. Remember this order, as it's crucial for getting the correct answer. Next, the constant c. You'll recall from our discussion on indefinite integrals that we always add a constant of integration, often denoted as c, to represent the family of all possible antiderivatives. However, when dealing with definite integrals, we can safely omit this constant. Why? Because when we subtract the value of the antiderivative at the lower limit from the value at the upper limit, the c terms will always cancel each other out. It's like having plus c and c, they eliminate each other. So, to simplify things, we just leave c out when calculating definite integrals. Now let's look at the formula. This is the heart of definite integration. The definite integral from a to b of a function f of x, which we write as integral from a to b of f of x dx, is equal to the antiderivative of f of x, which we call f of x, evaluated at b, minus the antiderivative evaluated at a. In other words, it's f of b minus f of a. This formula encapsulates the entire process we've been discussing. Finally, the sequence. This is a really common mistake students make, so pay close attention. When you're evaluating the antiderivative at the limits of integration, always substitute the upper limit first, and then subtract the value obtained by substituting the lower limit. So, it's always upper limit minus lower limit. If you reverse this order, you'll end up with the wrong sign for your answer. Think of it as big minus small. You want to subtract the smaller value from the larger one. So, to reiterate, integrate, then evaluate, omit the constant of integration, use the formula f of b minus f of a, and always subtract in the correct order. Master these key takeaways, and you'll be well equipped to tackle any definite integral problem you encounter.